Today we're going to continue our light fundamentals discussion. Our goal is to define luminous intensity, luminous flux, illuminance, and then solve some illuminance problems. The problems aren't so hard today other than you have to keep track of all the things that sound similar. So if you look at our bell ringer, how long would it take light from Michelson's experiment to get back to him? Well, we know that the distance between the two mountaintops was 35 kilometers, and velocity is distance divided by time. So if my speed of light is 3 times 10 to the 8th meters per second, and the distance was 35 kilometers, which is 35,000 meters, and you have to go from one mountaintop and back, the total distance for that 35 kilometers would really be 70,000 meters. How much time does it take light to travel 70,000 meters? So if you divide your 70,000 by 3 times 10 to the 8th meters per second, you get 2.3 times 10 to the negative 4th seconds. Let's look at today's stuff. Light fundamentals. Sources of light. The reason we see light is it hits our eyes, our retina. Our eyes interpret that image. But everything doesn't give off light. Things that give off light are called luminous. So a luminous body is something that emits light. An example of that would be something like a light bulb, the sun. Those are all luminous bodies. But we also see things that don't give off light, and those are called illuminated bodies. The reason they are visible is because they reflect light. The moon is an illuminated body. People are illuminated. We reflect light, and that's why we can see them. If you've ever gone to a cave, in the bottom where they've shut off all the light so there's absolutely no source of light, and you put your hand 6 inches in front of your face, you can't even see anything. Without light reflecting, you won't make or be able to see any object. Luminous flux is the rate at which light is emitted from a source. And the symbol for luminous flux is going to be P in our equations. So the rate at which light gets emitted from the source, how much light leaves. Luminous flux is measured in lumens, which is abbreviated LM. So those are just the SI units for luminous flux. And we know that light is emitted almost in all directions. So if you've got a light bulb, it's going to go off in every possible direction except directly where the socket is. The sun doesn't have a socket, so it's going to emit light in every possible direction. Here at school, we're less concerned about how much light is emitted from the source, and we're more concerned with how much light is being reflected on a surface. You know, how much light is on the table so you can read your books at a decent rate. And that deals with illuminance. Illuminance is the illumination of a surface. How much light is on the tabletop? The symbol for that is going to be a capital E, and that is going to be measured in lumens, so the amount of light per square meter. And that has a symbol of Lx, which stands for lux. We know that the surface area of a sphere is 4 pi r squared. The area of a circle is pi r squared, so the area of a sphere is 4 pi r squared. If you've got a bulb emitting light, it goes out in all directions, so that light gets divided amongst the whole sphere of influence, I suppose you could say. What happens to the illuminance the further you get? Well, it goes down. It varies proportionally with 1 over r squared. So if you have a certain amount of light, if you maybe have 10 lux 1 meter away, and you double your distance, you're going to have 1/4 as much, or 2.5 lux. If you triple the distance away, you're going to have 1/9 as much. Well, 1/9 of 10 is a little over 1. So it's an inverse square law. Luminous intensity is the amount of flux that falls on exactly 1 square meter of a sphere, 1 meter in radius. So if you can imagine a sphere, 1 meter in radius, that would have a total area right here, 4 pi squared times, or 4 pi r squared. 1 squared is just 1. So that would have a total of about 12 square meters. So 1 square meter of the 12 would be the amount of flux. So how much flux falls on 1 square meter of a sphere, exactly 1 meter radius? The units for luminous intensity are candelas, CD, which comes from the old unit of candle power. Used to measure how much light based on how light the candles were. So the SI unit of light intensity is the candela, or luminous intensity. You can find the luminous intensity very simply by taking your flux divided by 4 pi, because the flux is the total amount that's given off, and the intensity is how much falls on exactly 1 square meter with a radius of 1. So if you have that radius of 1, divide it by 4 pi, and you would end up with your candelas. So let's pretend that the OSHA friends come over and want to determine if we have enough light on our tables. And they decide, you know what, there's not enough light. Well, what are some things you can do to increase the illumination on a surface? Well, obviously, one thing you could do is just have a stronger light bulb. So somehow you could increase the luminous flux of the source. Maybe double the number of lights you have in the ceiling. Or maybe buy higher wattage bulbs, but somehow get more light from the source. What else could you do? Well, since we know that the illuminance is proportional to the 1 over r squared, you could actually decrease the distance between the source and the surface. So if you bring that light bulb closer to the table, maybe have a drop ceiling so the lights are closer to the table, that would also increase the amount of illumination. Here's a couple equations. E is the equation for illuminance. And to find your illuminance, all you have to do is divide your luminous flux by 4 pi, the distance to that source, squared. And like we mentioned, to find luminous intensity is simply your flux P divided by 4 pi. Now the equation for illuminance is only valid for point sources. What that means is if I've got a light bulb and I want to figure out the illuminance out here, no problem, because we know the light goes every possible direction, so I can measure how much light falls on this table. If we have a fluorescent bulb and I want to measure the illuminance on this table, well, some of the light from here hits the table and some from here hits the table, and so on and so on and so forth. So your distance is changing throughout the whole length of that bulb. You could solve for that amount of illuminance, but that would require a little bit of calculus and some functions. But that would be a good exercise for you to do as well. Let's look at a couple example problems here. First one, a typical 100-watt light bulb emits 1,750 lumens. What is the illuminance on a sphere with 1 meter radius? Well, illuminance, we know, is P divided by 4 pi d squared. So what is the illuminance on a sphere of 1 meter radius? Well, take your 1,750 lumens divided by 4 pi times 1 squared. And when you multiply that out, 1,750 divided by 4 pi times 1 squared, you get 139, and the units are lux. What's going to happen if you increase the radius? Well, now your radius is just 2 squared, or 1,750 lumens divided by 4 pi times 2 squared 4. You end up with an illuminance of 34.8 lux. Something else you could have done, since it's an inverse square law, if we double the distance, this answer should be exactly 1/4 of whatever the original one was. And you can see that it is. There's a second problem. The same light bulb has this much flux. How much luminous intensity is there? Well, luminous intensity is simply flux over 4 pi. Our 1,750 lumens of flux divided by 4 pi would equal 139 again, but since this is luminous intensity, the units are candelas. And one final example, a bulb with 1.5 candelas of intensity has what flux? Now we just want to work backwards. So luminous intensity equals P over 4 pi. If my luminous intensity is 1.5 candelas, that equals my flux over 4 pi. So in order to find my flux, you just need to multiply both sides by 4 pi. And then you'd end up with P equaling 19, and the units for flux are lumens. Don't put the units too close, or it looks like you have 191 meters when we know it's really 19 lumens.